Hi, everyone, and welcome to Hot Test, third talk of the fall 2020 season, I believe. And it is with great pleasure that I introduce Yuki Maehara, who will speak about the cubical model for weak omega categories.
Thank you, Chris, for the introduction and also for the invitation. So yes, I will be talking about this cubical model for weak omega categories today, which I developed with Tim Campion and Chris Kapulkin a few months ago. And all right, so I mean, this talk is about weak omega categories, but let me start the talk by recalling the strict omega categories. I mean, the omega here is the limit ordinary omega. So the ordinary categories are one categories, and you might be familiar with the notion of two category, three category, and so on. And so these omega categories are the sort of the limit case of that. So if you have an omega category, then just like ordinary categories, we have objects or zero cells, which look like points. And we have morphisms or one cells, which look like arrows. And we can compose these things in the usual way. And this composition is, well, unital and associative in the strict sense, so up to equality. And well, if you have an ordinary category, then that's it. But if you have, say, a two category or more generally an omega category, then we can have two cells between a parallel pair of one cells, which you can compose either horizontally along a common zero cell or vertically along a common one cell. And generally, we can, have for any, I guess, non-negative n, n cells which are shaped like the n-dimensional globe. So we have two objects, and then we have two arrows connecting them, forming a circle, and then two cells, so two disks bounded by this circle, hence forming a sphere and so on, all the way up to a pair of n-1 cells, between which is your n-dimensional cell. And these things you can compose in n different ways. And well, yeah, so this is the, I guess, the most standard definition of omega category. Maybe I should say that if you take the single sorted sort of definition of omega category, then you can actually talk about sort of infinite dimensional cells. But for this talk, I am not allowing these things. So all cells in my omega categories are finite dimensional. Anyway, so that is the definition of omega category, but this is globular, as it says up here, because, well, the cells are shaped like globes. But today we are interested in a cubical approach to these omega categories. So now let me give you a cubical version of all of this. So, I mean, in that setting, instead of these globes, we should have cubes. But I mean, the zero-dimensional cube is just a point, and the one-dimensional cube is just, well, a line. So up to here, everything is the same. But now the two cells should be shaped like the two-dimensional cube, which is, well, a square. So here's what a typical two cell would look like. And again, you can compose these things in horizontal and vertical directions. But this time, both of these compositions are along a common one cell. And so these pictures might remind you of double categories if you, if you know about double categories. But double categories are different from these cubical, say, two categories. And the difference is that if you have a double category, then you have a set of objects and then a set of horizontal morphisms and a different set of vertical morphisms. But in this setting, we only have one set of one cells. So although in this picture, we have sort of two arrows pointing to the right and two arrows pointing down, all of these one cells come from the same set of one cells. Anyway, so here is what a typical two cell would look like in this setting. And in general, we can again have n cells for any finite n, and these would be shaped like the n-dimensional cube. And we can compose them in n different ways, basically stacking these n-dimensional cubes in n different directions. Right, so these, so this is the definition of cubical omega category. And I say with connections up here. And so again, if you know about double categories, or alternatively, if you know about cubical sets, I guess, and these are the sort of the connections that you see in these things. But if you're not familiar with these connection thingies, then don't worry too much. It won't be that important for this talk anyway. I mean, for like the actual mathematics, it is important that we have connections, but for this talk, it's not. Right, so now I have given you two different notions of omega category. And now it's the theorem of Al-Agl, Brown, and Steiner that these two notions are equivalent, well, in the sense that they give rise to equivalent categories. So the category of globular omega categories is equivalent to the category of cubical omega categories. By the way, I have color-coded everything so that throughout this talk, blue means globular and green means cubical. And I hope that that helps. Anyway, so anyway, these two categories are equivalent. And I will not go through the whole proof, but I will at least show you how you can construct the functors going either way, giving you this equivalence.
Yuki, can I interrupt?
Yep.
Sure. So firstly, these are strict globular omega categories and strict cubical.
That's right. Yep.
Okay, and the compositions in the cubical omega categories, are they just sort of like pasting cubes together? Or
That's right.
Okay.
Yeah.
Okay. I mean, is it like filling general? I mean, I know what the geometry is in your setup, but I'm wondering what the geometry is for this result. I mean, there's no marking of invertible simplices or anything like that. So
no, I mean, yeah. So this is.
Or what are we talking about?
So what? This is so I guess a cubical set with connections with the sort of unitary and associative compositions in every direction, and these connections needs to sort of be compatible with the compositions and that sort of, yeah.
Right. I see. So the thing that I was confused about before is if we're trying to define a strict cubical omega category, when I'm composing one cubes, I don't need to involve the two cubes at all. I can just
Yeah.
one cubes. Got it. And likewise in higher dimensions. Thanks.
Yes. Cool. Any other questions? I sort of see the notification that there's something going on the chat, but I guess unless Chris says something, I don't have to worry about it.
Yeah, don't worry about it. If there's anything that's not us joking about certain things, then you'll be notified.
Yeah, sure. Cool. All right. What was I saying? Right. So we right. So to get the functors going, well, between these two categories, what do? Well, so say we want to go from globular to cubical. Well, I mean, whenever you want a cubical sort of thing, you look at whatever you're given, and then you sort of, try to find all kinds of cubes in there. So you probe whatever you're given with cube-shaped globular omega categories. And that should give you a functor going from the globular to the cubical world. And to go back from cubical to globular, well, I mean, you basically do the same thing, but with globes and cubes swapped. So now you probe whatever you're given with globe-shaped cubical omega categories. And I mean, I will show you pictures of these things in the next few slides. So starting with the cube-shaped globular omega categories. So for each dimension n, we want the n cube realized as a globular omega category. But again, the 0 cube is just a point, and the 1 cube is just a line. So this is just a terminal thing, and this is just the generic arrow category. Oh, by the way, my notation is that the n-dimensional cube-shaped thing is I to the n. I will have to refer back to these things later. But anyway, so these are the 0 and 1 dimensional things. And in dimension 2, now we should have a square. So this is, I mean, I have basically given you the same picture as a typical 2-cell in the cubical world. I mean, I guess I actually copy and pasted this picture. But now this is drawn in blue. And that is to remind myself, to remind you that we are in the globular world. So this picture should be somehow interpreted globularly. In particular, this middle 2-cell should really be a 2 globe. So what this actually means is that, well, we have these 4 generating 1 cells. And because we are in an omega category, we can say compose these 2 arrows and get a composite arrow going from top left to bottom right. Similarly, on the other side, and this 2-cell in the middle is really living between these 2 composites. Well, similarly, in dimension 3, here's what the I3 looks like. So we have this cube with, good accounting, 12, I guess, generating 1 cells and 6 generating 2 cells. And you can compose these things in, well, a suitable way. I mean, there's really only one way to compose these 3 into a single 2-cell. And on this side, again, there's really only one way to compose these things into a single 2-cell. And then this 3-cell in the middle is living between these 2 composites. So, I mean, they do look like cubes, right? Anyway, so these were the cube-shaped globular omega categories. And now to go the other way, we need globe-shaped cubical omega categories. And I mean, I will skip the 0 and 1 dimensional ones because they'll just be the same pictures. And in dimension 2, here is what the thing looks like. Modulo some subtlety that I'm crossing over, but this is the generating data anyway. So we have this single 2-cell, which is now shaped like a square because we are in the cubical world. But this 2-cell has the top and bottom boundaries identities. So if you collapse these edges, then this does indeed look like a 2 globes. And similarly, in dimension 3, here's what the thing looks like. So again, this is a single cube with lots of identities on its boundary. But if you look at the 6 faces of the cube, for example, the top face here is really the identity 2-cell on the identity 1-cell on the object. So this whole face you can collapse to a single point, which corresponds to the top point here. Similarly, the bottom face here you can collapse to a single point here. And so the face on the right here is the identity on G. So this is really just this 1-cell going down G here. And similarly, on the opposite side is this F going again from top to bottom. And we also have alpha going from F to G and beta going from the F to G. So these boundary faces correspond to these 0, 1, and 2 cells in here. And finally, the interior 3 cube here now corresponds to the interior 3 globe here. So these are the globe-shaped cubical omega categories. And yeah, so mapping out of these cube and globe-shaped things, we get an equivalence between these categories of omega categories. Now, so I mean that's a cool theorem, but now what? Well, so now we have 2 different ways of looking at these omega categories, and I mean maybe more precisely, we have 2 different kinds of shapes that we can use to think about omega categories. And different shapes are good for different things. So for example, in the world of globes, somehow the fundamental construction on globes is taking the 2-point suspension. So if you take the 2-point suspension of the n globe, then you get the n+1 globe. And this, so this construction is, in some sense, fairly useful for sort of thinking about enrichment. So, I mean, in at least the globular case, it's fairly obvious, and it's sometimes even the definition that the n+1 categories are the categories enriched in n categories. Well, at least if you sprinkle small everywhere. But I mean, because we have this equivalence, it should also be true that the cubical n+1 categories are the categories enriched over the cubical n categories. But I have no idea how that actually works. I mean, other than, via this equivalence, that should be true. Anyway, that's one thing that is much clearer from the globular viewpoint. I guess a related thing is the duality. So on the globes side, I mean, you can just reverse all the n cells for some fixed n, and that will give you a duality on the omega categories. But on the cubical side, while preparing for this talk, I tried to come up with a nice conceptual explanation, but I couldn't really come up with any. But it just seems to be the case that you can really only see 2 kinds of dualities on the cubical side. Yeah, which is a bit annoying. But I mean, the cubes are good for something else. So what is it actually that the cubes are good for? Well, just like the fundamental construction on the globes is taking the 2-point suspension, the fundamental construction on cubes is taking products. Well, I mean, if you take the product of the m-dimensional cube with the n-dimensional cube, you get the m+n-dimensional cube. So if you have a construction that at least geometrically looks like taking product, you might expect that thing to be easier to deal with from the cubical perspective. And well, what is an example of such a construction? Well, the gray tensor products. So these are the sort of tensor products that we want on omega categories. So there are 2 flavors, lax and pseudo, although for this talk, I will mostly focus on the lax version. But anyway, both lax and pseudo gray tensor products are some sort of less commutative versions of Cartesian product. So for example, if you take the Cartesian product of 2 copies of the one cell, you get just the commutative square. But if you take the Lax Gray tensor product of 2 copies of the one cell, we get, well, a square with a 2 cell in the middle. And now I am sort of being vague about whether this is a cubical or globular omega category, which I'm allowed to be because they're equivalent. And anyway, so here is, well, at least what the Lax Gray tensor product does on this particular pair. And so, I mean, these are the 1 and 2 dimensional cubes. So this is saying that I1, if you remember my notation, I1 tensor I1 is I2. And in general, this Lax Gray tensor product satisfies this IM tensor IN is IM plus N. So, well, this matches what happens with cubes. So the M cube tensor the N cube is the M plus N cube. And in fact, it's a theorem of Kranz that this Lax Gray tensor product can be characterized by this property if we further ask that this thing being part of a biclosed monoidal structure on omega cat. So this Lax Gray tensor product is the unique such thing. So yeah, so this is the Lax Gray tensor product, and the pseudo version, it's well, at least on 2cat, this is the sort of product we have. So instead of a square with a 2-cell, we get a square with an invertible 2-cell. And this is a sort of a homotopical replacement of the Cartesian product, I guess. Instead of the usual equality in the Cartesian product, we have an isomorphism in the middle. And I mean, these things are somehow inherently cubical. I mean, I guess this is one sort of justification of that statement. And yeah, also if you look at Gray's book, I guess, the way he defines this tensor product, you can find lots of pictures of cubes in there. Yeah, so these tensor products are somehow cubical, and yeah, so the one on omega categories, you can, I mean, I guess the easiest way of constructing this tensor product is to use the equivalence of Al-Agl, Brown, Steiner, and that's actually what they did in the last section of their paper. Because I mean, somehow in the cubical world, like what it should do is clearer and easier to write down. So you can sort of write down what it should be and check that it actually works. And so anyway, yeah, the point is that these tensor products, well, we want to deal with these things, and these things are easier to deal with cubically. And so our motivation for introducing this cubical model for weak omega categories is so that hopefully these tensor products are easier to deal with. So I mean, the weak omega categorical version of these tensor products are easier to deal with if we use a cubical model. And I mean, later I will show that, well, at least I will claim that that is indeed the case. Yeah, so any questions up to this point? All right then. Okay, so now to give you the definition of our model, I have to actually introduce yet another way of looking at these omega categories, but I promise this is the last one. That might actually be a lie, but anyway. So the idea of this third way of looking at omega categories is that, so take a cubical omega category, then forget all the composition structure. Then we get just a cubical set, whatever that is. And so somehow, if you take the underlying cubical set of a cubical omega category, that almost remembers the compositions in some sense. But I mean, it doesn't quite. So to actually recover the compositions from the underlying cubical set, we have to record like a tiny bit more, which is this marking business. And so yeah, so the idea of this third way is to look at this underlying marked cubical set and somehow recovering the compositions from that structure. Excuse me. Right. So now maybe I should make precise what I mean by cubical sets. So these cubical sets, again, I say with connections, but don't worry too much. These things are the presheaves on this category of cubes, which I think is easiest to describe as a subcategory of cat, although it won't be full. But anyway, this category is a subcategory of cat whose objects are, well, cubes. So these are the powers of the generic arrow category. The morphisms are generated by these 5 maps between the low dimensional cubes. So the 0 cube, which is just a point, the 1 cube, which is just an arrow, and the 2 cube, which is just a committed square. and these 0 and 1, just the endpoint inclusions. This is the unique thing to the terminal category. And well, these min and max things give you the connection things. Yeah, anyway, it's not terribly important exactly what these maps are for this talk, anyway. But what is important is generated under what? Well, I mean, we want a category, so we have to close this set under composition, but we also close it under taking products in cat. So, I mean, whenever you're given a pair of morphisms in this category with cubes, at least on the domain and codomain, their product would still be in this category of cubes. I mean, the object set is closed under taking products. And so we ask that the product morphism also be in the category of cubes. But this is taking products in cat. And so this is not the product in this category of cubes. So for example, we don't get the diagonal going from the arrow to the commutative square. But still this, I mean, we are like explicitly closing this category under this operation. So taking the m cube and the n cube to the n plus n cube is a valid monodal structure, strict monodal structure, assuming we are taking, well, within the, you know, we're only taking the skeletal thing. And so this is a monodal structure on this category of cubes, and we are looking at the appreciative category. So we can extend this by deconvolution, and we call the resulting thing the geometric product of cubical sets. So, so this taking products of cubes is the fundamental construction on cubes, and this geometric product is somehow the appreciative version of that. So in some sense, all the good features of our model should come from this geometric product. And I will make that a tiny bit more precise later. But anyway, yeah, I guess that's the slogan. All the good features of our model should come from this geometric product. Anyway, so this is, at least for this talk, what I mean by cubical sets. And now back to this third way of looking at omega categories. So if you take the underlying cubical set of a cubical omega category, then there are certain special cubes, namely those that correspond to identities, or at least globular, I guess, identities. For example, if we have a pair of composable morphisms F and G, well, we can compose them differently, and we get this another one-cell GF. And here, by equality, I mean the identity on this object Z. And in the middle, we can, well, at least globularly put the identity 2-cell on the composite GF. So somehow, I mean, yeah, so if you sort of see this globularly, this is just the identity 2-cell on GF. But if you really see this as a 2-cell in the cubical world, then this is not the identity on, I mean, either in the horizontal or vertical direction. I mean, it doesn't even have, you know, the same domain and codomain. And also, I mean, so that means in this underlying cubical set, it doesn't come from degeneracy, and also it doesn't come from connection. So somehow these cubes, I mean, they should be special, but we can't see that in this underlying cubical set. And an example in one dimension up is this. So here we have alpha, beta, gamma, 2 cells arranged this way, forming one side of the cube. And on this side, so these two faces, the bottom and the right ones, are basically of this form, this composing one cells. So these two faces are basically observing that this bottom boundary of delta is a composite of these two arrows, and the right boundary of delta is the composite of these two arrows. So these two faces are basically sort of filling the space to sort of pad out the boundary of delta to the boundary of this whole thing. But this is really, well, at least globularly, just saying that delta is the composite of alpha, beta, gamma. Although again, in the cubical structure, we can't see that. This cube is not identity or connection. So now this third way of looking at omega categories, what we do is we mark such identity cubes, and with this marking, we recover or encode the compositions using unique marked fillers for open boxes. So by an open box, I mean the boundary minus one of the faces. And for example, now I have grayed out this composite GF and also the interior. And so whenever you are given this pair of morphisms, we can put this identity here and form this sort of open box. And now we ask for such open boxes to have unique marked fillers. And what that's saying is, well, I mean, if the interior is supposed to be marked, then that will basically witness that whatever ends up on this edge is a composite of F and G. So asking for a unique marked filler for this particular open box is basically the same thing as asking for a uniquely defined composite of F and G. Similarly, in the three-dimensional example, now we have this open box where we are missing this left face. And again, asking for a unique marked filler for this, this open box is basically the same thing as asking for a uniquely defined composite or pasting of alpha, beta, gamma. So now let me make this a bit more precise. So now we are in a category of marked cubical sets. So a marked cubical set is a pair. So the first bit X is just a cubical set. And together with these marked cubes, so these are the subsets of these sets of cubes. So these marked cubes, they just form subsets, not cubical subsets. So they are not necessarily closed under taking faces, for example. And yeah, so these marked cubes should somehow correspond to the identity cubes that we had on the previous slide. So we ask these marked cubes to contain degeneracies and connections because, I mean, these cubes should have the identity sort of thing in the interior. And we only allow marked cubes of dimension 1 or above because it doesn't make sense to talk about zero-dimensional identity morphisms. So now this is the category that we are working in. Now it's a theorem of Steiner that a marked cubical set underlies a cubical omega category if and only if certain open boxes, by which I mean the sort of boxes that I showed you on the previous slide, these things admit unique marked fillers, hence encoding compositions. And moreover, these marked cubes compose. So compose in the sense of the composition encoded by these marked fillers. Yeah, so I mean, marked things should compose to marked things because the corpus of identities is still an identity. Except that I sort of misquoted this theorem. So this is not exactly what's in Steiner's paper. And I mean, if you're interested, then you can ask me later. But for this talk, I will pretend that this is the theorem because, well, it makes it easier to justify our model, I guess. But anyway, so here is, I mean, this theorem is a characterization of the strict omega categories, but we want weak omega categories. So what do? Well, I mean, whenever we want to, you know, we want to turn strict things into weak things, what we do is I mean, very informally speaking, just turning every single equality we see by a sort of higher invertible morphism, whatever the right notion is in that context. So in particular, in this setting, the marked cubes used to correspond to the identities in the strict case. So in the weak case, probably we want the marked things to correspond to invertible morphisms. And so if we take that viewpoint, what should we do? Well, I mean, we still want marked cubes to compose to marked things because a composite of invertible things is still invertible. And also we still want the existence of these marked fillers because that would encode the existence of composite, and we do want to be able to compose things in this omega category-like thing. But because now the compositions are witnessed not by identities, but by invertible morphisms, it doesn't make sense to ask for unique marked fillers anymore. So we just drop uniqueness. And let's go. That is our definition. So a comical set, comical being a shortening of composition, and cubical set. Anyway, a comical set is a marked cubical set in which these two conditions hold, except for the uniqueness bit. Right, so this is our cubical model in the title of this talk. Any questions? All right. I mean, all right, that's a definition, great. But so as our motivation for proposing this model, I mentioned the gray tensor products. So we expected the gray tensor products to be somehow easier to deal with this cubical model. So now let me introduce what these gray tensor products look like in our setting. So, I mean, but remember our slogan, the geometric product is where all the good features should come from. And in particular, what that means here is that the geometric product should underlie the Lax Gray tensor product. I mean, we want, you know, we want some analog of the M cube density N cube is M plus N cube. And I mean, the geometric product, it does precisely that. So, I mean, in some sense, this geometric product is the Lax Gray tensor product, or well, it should be. But this is not the whole definition because now we are in the category of marked cubical sets. Yes,
so Yuki, in the chat, there's a question. Are there any coherence conditions on the marked fillers? For example, do they need to be related by yet higher dimensional marked cells?
Right, so this is sort of the combinatorial magic of open boxes, or like inner horns, or these sorts of things. They somehow encode these coherence as well. I must say, I don't really see why it should, but I mean, you can sort of, at least in low dimensions, and you can draw like horns or boxes that exhibit somehow these compositions, uniton, associative, and everything. Yeah, so so I guess I was slightly misleading in saying that these open boxes, I mean, fillers for open boxes encode compositions. They somehow encode much more, including the coherence conditions. Does that answer the question?
Ed, the question comes from Ed Morehouse. Does that answer your question? Yes, thanks. Okay.
Okay, cool.
Go.
All right. So what was I saying? Right, so the Lax Gray tensor product. Right, so on the underlying cubical sets, this Gray tensor product is just given by the geometric product. excuse me, but now we have to worry about the markings. So for example, what happens if we tensor the marked one cube with the unmarked one cube? The marking doesn't, shouldn't change the underlying cubical sets. Somehow, yeah, back to the slogan, the geometric product is where everything should come from. So we do want the underlying cubical set of the tensor product to still be just the 2 cube, but now we should probably mark some cubes in here as well. So exactly which cubes in here should we mark? And so you can actually figure out quite a bit by using, the first thing is, I guess, a fact that, we are defining morphisms of marked cubical sets to be, well, morphisms of cubical sets that preserve the marking. And we, now we want this tensor product to be functorial. I hope that sounds reasonable. And another thing is that we want the 0 cube to be the unit for this tensor product. And just from these 3 conditions, we can figure out, for example, that, all right, so there are 2 morphisms from the 0 cube to this second factor. So these are the inclusions of the top and bottom points. And because we want this tensor product to be functorial, now we can tensor that these 2 morphisms with this first factor. And because the 0 cube should be the unit, these should induce morphisms from this first factor into whatever this tensor product is. So that, they are just the inclusions of the top and bottom edges. And now these morphisms of marked cubical sets should preserve the marking. So we should send this marked one cube to these top and bottom cubes. So they need to be marked in the tensor product as well. And also we can consider the morphism from this first factor into the 0 cube. And again, we can tensor that with this object. And that should give you basically the projection of this tensor product to the second factor. And that projection is sending both of these downward pointing arrows to this unmarked one cube. So that implies that we must not mark these vertical morphisms. So that leaves only this 2 cell in the middle undetermined. And to figure out whether we should mark this thing or not, now we actually have to think a bit more about what the gray tensor product is supposed to do, and also, I guess, what the marking is supposed to do. About the marking, I said that the marking should indicate that this cube is invertible in some sense. So let's just imagine having an inverse to this marked morphism. And similarly, these 2 marked cubes in the square should have inverses. So these cubes don't actually exist in these cubical sets, but we are sort of just imagining these things being there. Well, so this imaginary left pointing arrow, we should be able to tensor that with this second factor and get something like this, where the top and bottom boundaries are the imaginary things here and here. And well, now because we are in, well, something like an omega category, we should be, so I'm drawing now this arrow this way, so it's pointing from the lower path to the upper path, so we can draw it this way. We should be able to whisker or compose this 2 cell with the orange arrows, because we are in something that at least is trying to be an omega category. So now by composing with these orange things, we should get something of this form. But I introduced the left pointing arrows as the inverses to the orange things. So the composite here should cancel out, and also the composite here should cancel out. So in the end, we have this morphism from this top path to the bottom path. So this two cell, I mean, this is imaginary, but this is somehow supposed to be there. And this is pointing in the opposite direction from what we had here originally. And if we were actually in an omega category and this was the actual gradient tensor product, then you can do a little more argument and then deduce that what we have here is in fact an inverse to this original two cell here. And well, I said the marking should indicate that the cube being marked is invertible, and we just constructed something like an inverse. So we should probably mark this two cube in the middle as well. And that completes the definition of the gradient tensor product, at least of the marked one cube and the unmarked one cube. And in this picture, you can actually see that the marked cubes in here are precisely those that geometrically project to this marked one cube here. So in other words, if you are moving horizontally, then you are marked, and otherwise you're not. And in fact, that is the general definition that we take. So now the formal definition, the Lax Gray tensor product of marked cubical sets is given by, well, so remember, a marked cubical set consists of a cubical set and a subset of the marked cubes. And well, on the underlying cubical sets, this is just the geometric product. And a cube in this geometric product can be always written as a cube in the first factor tensor a cube in the second factor. And now we mark this cube if and only if either x was marked in x or y was marked in y. So in symbol, here is well, the set of marked cubes in the gray tensor product. So these are the cubes that have at least one marked factor. And the pseudo gray tensor product, I won't go through the sort of same sort of motivational example, but basically in the pseudo gray tensor product, somehow it should more or less be the Cartesian product. So the intuition here is somehow we should basically mark all the cubes that would be identities in the Cartesian product. And if you make that precise, this is the condition. So actually for the pseudo gray tensor product, it's easier to describe what the unmarked cubes are. And these are precisely the ones of the form unmarked tensor zero cube or zero cube tensor unmarked. Right. So now I have given you, well, a sort of vague definition of our model and maybe more precise definitions of these gray tensor products. And I mean, I mentioned the gray tensor products as our motivation for developing this cubical model, so that better interact nicely. And what that means in this context is the following. So as well is usually the case with this sort of higher business, we have this model structure on the category of marked cubical sets, where the cofibrations are the monomorphisms and the fibrant objects are the comical sets. Our model for weak omega categories. And this model structure is monoidal with respect to both Lax and pseudo gray tensor products. And I mean, this, the proof of this does, require some combinatorics, but the combinatorics is relatively easy. I see Chris is laughing, but I mean, this is actually, relatively easy, right? And the sort of maths that we have to show to be trivial cofibrations are like just push-outs of generating trivial cofibrations. So like there's no sort of transfinite composition business. It's just a single push-out. So I insist that this is easy.
No, for me, combinatorics is hard or impossible, and that translates to easy and hard for you, I think, and that's the reason why.
I guess that's the difference between Australian and Canadian English. Maybe not. Anyway, so the proof is relatively easy, and I mean, in fact, a bit. Nope. I decided not to talk about that. That's too much combinatorics. Anyway, so
look at that. Too much combinatorics.
I mean, yeah. I mean, some combinatorics are easy for paper, but probably too much for a 60-minute talk. Anyway, so this is, I mean, one of the main theorems we have in our paper. And in the remaining, I don't know how many minutes I have, 10 minutes or something?
8, 10.
Yeah. I will talk about how this model compares to the simplicial precursor. So basically, everything not quite everything we did, but everything I've talked about so far has a simplicial precursor. And so, I mean, this setting, what corresponds to the comical sets, the complicial sets, so the strict version, I guess, was originally proposed by Robas, and the weak version has been, well, quite intensely studied by Verity. Anyway, so a complicial set is a marked now simplicial set in which suitable horns admit marked fillets, so encoding compositions and coherence in a similar way. And these marked simplices compose. And so this is again, excuse me, this is again a weak version of what is equivalent to omega categories. So it's a theorem of Verity that the category of strict complicial sets is equivalent to the category of omega categories. So this is, I guess, the fourth way of looking at omega categories. And now this is the last one. But anyway, so in our paper, we compare our cubical model to this simplicial model using the triangulation functor. So triangulating cubes into, I mean, triangles, I guess. So what we do, I mean, the first definition. So, I mean, we want to send cubes to triangulated cubes, but also we need to worry about the marking. So the idea here is that, well, the n cube, the n-dimensional cube, is the Gray tensor product of n copies of the one cube. And probably the triangulation of the one cube should be the one simplex. And on the simplicial side, we have the Gray tensor product defined by Verity. So we just send the n cube to the simplicial Gray tensor product of n many copies of delta 1. I mean, I will not give you the precise definition of the simplicial Gray tensor product, but at least in dimension 2, here's what this thing looks like. So on the underlying simplicial sets, this tensor product is just a Cartesian product. So the Cartesian product of, I mean, 2 copies of delta 1 is just this square with a diagonal and two simplices pointing away from each other. But this Gray tensor product, well, does something on the marking. And in this particular example, it ends up marking one of the 2 simplices. So now this marked simplex is basically saying that the diagonal here is the composite of these 2 arrows. So basically this picture is more or less the same as this picture on the left. So it probably makes sense to send at least 2 cubes to this what delta 1 gray squared. And in general, if you take this tensor product of n copies of delta 1, it has a unique unmarked n simplex, which I'm calling iota n. So in dimension 2, this unmarked T simplex is iota 2. And so this somehow corresponds to the unique n cell in the n cube or in the in, if you still remember my my notation. And now, well, I gave this thing a name because, I mean, so now we also have to figure out where to send the marked n cube. But the marked n cube is, well, the n cube with the thing in the middle marked. And I just said that this thing in the middle corresponds to iota n. So we just send marked n cube to this same object, but with the last unmarked thing marked. So again, in dimension 2, this is what it looks like. So now both of these pictures are basically commutative squares after homotopy. Yeah, so basically, I mean, these conditions plus the co-continuity determines what the triangulation has to do. And our second, I guess, main theorem is that this triangulation factor is left-quelling with respect to our comical model structure and Verity's complicial model structure, and it preserves both lax and pseudo-gray tensor products up to homotopy. Yeah, so I mean, making this precise is a bit cumbersome because the gray tensor product on the simplicial side is not as well behaved, I guess. But I mean, this is essentially what we prove. And yeah, yeah. But anyway, this is, I guess, the end of what I prepared for the talk today. So thank you very much.
All right, thank you very much. So we're gonna now thank Yuki without unmuting our microphone. So yeah, just silent applause. Thanks a lot.
Thank you.
That was great. And yeah, we now have up to 31 minutes for questions. So if you have a question, feel free to deliver it in any way you'd like. Unmute yourself and just ask the question, raise your hand, write it in chat, and with my limited reading abilities, I'll do my best to read it. And so in chat, Ed asks, aren't there in general many marked n cubes differentiated by the pattern of marking on their boundaries?
Oh, right. Yeah, so by the marked n cube, I meant somehow, yeah, you know, the one where only the interior thing is marked. Yes, you can mark more cubes, and I guess you get what, more marked n cubes, but you can obtain such things, but I mean, as a sort of a co-limit of the unmarked and marked cubes. So yeah, so in that sense, it suffices to just define triangulation on these particular things.
Ed, we good? Thanks. Okay, so we're good. Okay. Any other questions? I'll just wait a bit. Well, maybe I'll ask a quick question. So you said earlier, you know, you admitted that you were lying about one theorem. I believe it was the theorem of Steiner, right? Which is,
yeah, that's
admission of lying is already more than we would expect from a presidential debate. So it's, yeah, if you want to comment on that now that you build all the.
Right, so this is the theorem. Well, okay, this is the non-theorem, I guess. And right, so what is the actual theorem? So what Steiner actually did was he characterized the underlying marked semi-cubical sets. That's the word, right? Where you only have the face operations. And so in addition to open boxes, he also asked for unique marked fillers for certain boundaries. And that way he recovered the degeneracies and connections. So yeah, I guess, I mean, this is more or less a guess from sort of Nixon, Steiner's and Dom's results, but if you want to actually characterize the underlying cubical sets, then probably you need to add that the marked one cubes are precisely the degenerate ones or something. Yeah, so I mean, and I think we have a good reason like to actually use cubical rather than semi-cubical sets, which is I mean, so yeah, in that paper, Steiner sort of suggests that, you know, because in a sort of weak context, you might want to think about identities that are not really sort of, you know, privileged as connections or degeneracies. So it might be more natural to sort of look at just semi-cubical sets and ask for non-unique fillers for these boundaries and recover identities that way. But at least I couldn't really see how that was supposed to work, because if you do sort of the obvious analogous thing, then I think you'd basically end up saying, for example, any two parallel marked one cubes are like are homotopic or like connected by a marked two cube. Like somehow you can't really distinguish yeah, what I'm trying to say. Yeah, I mean, if you just try to write sort of I mean, yes, if you just write down the same thing but without uniqueness, then you are asking way too much than identities or identity-like things. And yeah, I can really figure out how to make that work.
Okay, anyone else? Any other questions or comments? Okay, maybe I'll ask one more question.
Okay.
So you didn't comment much on connections. So in the type theory community, you know, there's a big schism of connections versus no connections. So
right. So I mean, we definitely need something like connections to move between different directions. I mean, for example, in the strict case, I guess the cubical omega categories without connections are not equivalent to the usual omega categories. But from our open box fillers, I think we can sort of get connection-like things even if we didn't have them to start with. So I don't know, maybe somehow we can do without them. I mean, not actually without them, but like we can sort of recover them even if we didn't have them at the start. But I don't know. I mean, okay, so at least for what I talked about today, that is probably the case. But for other things that we are trying to do, we do sometimes want sort of strict equalities and things. So I don't know. It's probably more convenient to have connections, although there might be a way around it.
All right, last call for questions. Okay, if there are no more questions, then let's thank Yuki again.
Thank you.
And thanks. That was great. So